All right, this is continuing section 1.3 of Math 146. Um, we are still in the ideas of using factoring to simplify. So we are going to continue our examples. Um, we're going to have example 8, which looks like x over x squared plus 3x plus 2. And we want to add that to 2x minus 3 over x squared minus 1. And again, remember the idea that we had on the very last problem that we did, example 7, was that you can always multiply the two denominators together to get a common denominator to add or subtract these fractions. However, in this case, that is not going to be the most efficient way. Multiplying those two things together is going to create a mess. So what I always like to tell people, and you will probably hear me say this through the course, it is better to make things a little smaller first to see what you have, and then sometimes you can go from there to make it bigger, but make things smaller before you go bigger. So let's factor what we can. Let's factor the denominator of the left. That would give us x plus 2 and x plus 1. Okay, and then let's factor the denominator on the one on the right, which is a difference of squares, which will give us x plus 1 and x minus 1. The reason that that's good is because what you can see is both of these denominators already contain the same factor of x plus 1. That's already there. So I don't need to add, or I don't need to include another x plus 1 in either one of them. However, the one on the left-hand side is missing the x minus 1 from here. And the one on the right-hand side is missing the x plus 2. So the entire common denominator here, the least common multiple of these denominators, is going to be factors of x plus 1, which they both have, x plus 2, and x minus 1. So in the case here, we are missing the x plus 2 on this one. So we'll multiply the top and the bottom by x plus 2. And on the one on the left, we are missing the x minus 1, so we'll multiply the top and the bottom by x minus 1. That is an x minus 1 down there. Sorry. And now what you can see is the denominators are identical. So let's go ahead and do that. So we'll have for the denominators x minus 1, x plus 2, and x plus 1. We'll have that for both of the denominators. X minus 1, x plus 2, x plus 1. And now we can go ahead and distribute out the numerators before we can combine the like terms. So let's see, on the first one, we're going to get an x squared minus x. And on the other one, we will have to FOIL that. Again, think of that being in parentheses. So that's going to give us 2x squared. Let's see, we'll get a 4x and a minus 3x, so that'll be plus x. And then we'll have a minus 3 times 2, which is minus 6. Now the denominators are identical. Let's go ahead and combine like terms. So we're going to get 3x squared on top. Minus x and plus x goes away. That's nice. And then minus 6 over x minus 1, x plus 2, x plus 1. And once again, we're trying to get this into its simplest form. And as it appears that we can factor out a 3 from the numerator, which will leave us with an x squared minus 2. That is not going to factor any further since 2 is not a perfect square. So then you're just left with x minus 1, x plus 2, x plus 1 in your denominator. And that one there is about as simplified as we're going to get it. And your denominators can't be, let's see, 1, -1, and -2. So I think that's probably about as good as we're going to get there. All right, 2 more examples. of simplifying like this before we get to rational exponents and simplifying radicals. Um, this is going to be 1/2 plus 3 over x all over x plus 3 divided by 4. So not only do we have a compound fraction, we have fractions that are being added in the numerator together. So there's multiple ways you could go about doing this as well. You can, by all means, treat this as kind of separate problems. Combine the two numerators together. Combine the 1/2 and the 3 over x by getting a common denominator and changing those fractions and basically creating one big fraction on top. And then you can use the process that we did earlier where you had one big fraction divided by another big fraction where you bring the bottom fraction up, flip it over, multiply by the reciprocal, and then go that way. Or we can choose to try and get rid of all the compound fractions at once. So what you want to do is you want to look at the denominators of all the pieces. So let's look at the denominators here of all these pieces and ask ourselves, what is the least common denominator between 2x and 4? Well, obviously 2 goes into 4, so 4 is part of your least common denominator, and x is just x. So the least common denominator here is going to be 4x. And why is that important? Because what I can do is I can multiply the top and the bottom of this thing by 4x. So if you multiply 4x times 1/2, you're going to be left with 2x. If you multiply 3 over x by 4x, the x's are going to cancel out and you're going to be left with 12. And in the denominator, if you multiply the x plus 3 over 4 times 4x, the 4's are going to go away and you're going to be left with x times x plus 3. Now, the only other thing we can do is to factor that numerator, which I can factor 2 out, and that'll leave me with x plus 6 over x times x plus 3. Nothing else is going to divide out or cancel out, so that is the most simplified. But as you can see, we got rid of all of the compound fractions at one time just by multiplying by the least common denominator of all of them, or the least common multiple of all of the little fractions. So that's a very convenient way to do that. Once again, you would have some domain issues in the fact that x in this case could not have been 0, to start with. And when we get to the very end, it actually creates another one where x cannot be -3 as well. So those are two domain issues that you would have to take care of. All right, one more example like this, and then we'll get into the rational exponents. So our 10th example, I know it's a lot of examples. Let's see, we've got x squared over x minus 4, and then plus 2, all over 2x minus 2 over x, and then minus 1. Same principle. In this case, technically that plus 2 and the minus 1 are not technically fractions, although you can write them both over 1 so that it creates fractions, but you don't have to worry about that. We're looking for the common denominator of the little fractions, which is going to be an x minus 4 times an x. So we're going to multiply the top and the bottom by x. It's supposed to be in green. X, why is that in blue? X, there we go. X minus 4 and x minus 4. So multiplying that first fraction on the upper left, x squared over x minus 4, times the x minus 4. X minus 4s are going to go away. You're going to have an x squared times an x, which will give us an x cubed. Multiplying the 2 times the x times x minus 4 will give you a 2x times x minus 4. On the denominator, multiplying the x minus 4 times the 2x minus 2 over x, the x's will go away, and that will leave you with 2x minus 2 times an x minus 4, and then multiplying that by the minus 1 leaves you with a minus x times x minus 4. Now we can go ahead and distribute everything out, combine like terms, and see what we come up with. Whether we can refactor or not, we'll find out. So I've got x cubed, excuse me, plus 2x squared minus 8x all over, let's see, we got a bunch to do on the bottom here. That's going to be a 2x squared. That'll be a negative 8x, and a minus 2x will be minus 10x plus 8. And then distributing the last piece is a minus x squared plus 4x. All right, let's combine like terms the best we can. We'll have x cubed plus 2x squared minus 8x all over, let's see, what are we going to get there? 2x squared minus x squared is x squared. Minus 10x and 4x is minus 6x. And plus 8. All right. Now let's see if this stuff factors and simplifies it all. We can definitely factor a common factor out of the numerator, which is going to be x, which is going to leave x squared plus 2x minus 8. And the denominator, let's see, is that going to factor? Let's be 4 and 2. Yes, that will factor. That's going to be an x minus 4 and an x minus 2. And does that numerator factor any further? Combination of a 4 and a 2. Yes, it does. So we're going to have x times, let's see, this will be x. It's going to have to be a 2 and a 4. The 4 will have to be positive and the 2 will be negative, divided by x minus 4, x minus 2. And lo and behold, after all that, the x minus 2's are actually going to cancel out. Oops, that should be in red. So let's see. That should be our most simplified answer. And once again, you have to go back to figure out your denominators. Your denominators here could not be, let's see, what, 0, 2, and 4, I believe, are the things that were in the denominators that we have to be careful about. So yeah, that's it for those examples. Now we're going to move into rational exponents and how to simplify roots. All right, let's go ahead and start a whole new page for this. This one actually won't take as long as the last part. So we're going to be talking about nth roots and rational exponents. So nth roots, we're used to using square roots. Hopefully most of us are used to using cube roots. But they could be any number really in the root there that we want to, any whole number in the root there that we want it to be. It could be a 4th root, 5th root, 6th root, and so on. So those are nth roots. And then rational exponents are going to be things where your exponent is not just necessarily a whole number, could be a fractional exponent, like something raised to the 1/2 power or the 2/3 power. And things like that. So let's go ahead, or negative exponents, I forgot to mention that. Let's go ahead and look at some examples and how we work this stuff. So first thing is, let's go ahead and define how we write a root as a rational exponent. So if you have an nth root of something, we'll say it's the nth root of a. That is the same thing as saying that a is being raised to the 1 over n power. So, for example, if you have the square root of a, and we don't usually put the 2 in the index, this piece right here is called the index, then that would be the same thing as a to the 1 over 2 power, or a to the 1/2 power. If you have the cube root of a, that is the same thing as a to the 1 over 3 power. The general idea is that when you write a rational exponent, this top number here is the power of a, and the bottom number is the root. It is always the power divided by the root when you rewrite them. And then, of course, that process goes backwards. If you want to go from a rational exponent to a root, you just take that process backwards. If n is odd, the principal root is going to always just be whatever the root is. In other words, the nth root of a to the n power, because the root and the power would be the same if n is odd, would just give you a. If n is even, like the square root or the fourth root or the sixth root, then the nth root of a to the n power is actually going to equal the absolute value of a. Because what we should know is that if you take the square root of 4, technically a 2 or a -2 would work to give you the original value, but we want that to be the absolute value, which is, this is called the principal root. Principal root. When all it is that you're just doing is taking and simplifying a root. You're not using it to solve an equation or something like that. You're just simplifying a root. So when you take the even root of something, it will always end up being a positive value because you're taking the absolute value of the thing that's underneath. You can obviously use your calculators to do roots that aren't perfect roots or even perfect roots, but we're going to focus on how to do this stuff without using the calculator and simplifying roots to the best of our ability. So if we want to simplify the square root of 32, we actually did something like this in one of our other examples in a previous section. What you're looking for is you're looking to see whether there's any perfect squares that go into 32. And 4 goes into 32 evenly, and 4 is a perfect square. There's a bigger one, though. 16 goes into 32 evenly. So we could rewrite this as the square root of 16 times 2. But the square root of 16 is something that we know, and we can split that up using properties of roots to be the square root of 16 times the square root of 2. And the square root of 16's principal root is 4, absolute value technically of it, which is 4. And then the square root of 2 cannot be simplified any further because there are no factors of any perfect squares that go into 2 other than 1, and 1 doesn't do us any good. We can do the same idea if we take the cube root of something. Let's take the cube root of 16. 16 is not a perfect cube, but there are perfect cubes that multiply into 16. So that would be an 8. So we could separate that to be 8 times 2 underneath the cube root, which then can separate to be the cube root of 8 times the cube root of 2. And the cube root of 8 is 2, so we get 2 times the cube root of 2. All right, there are some slightly more complicated things for us to deal with there, but I think, you know what, let's do one more. Let's do one more example just of this so we can see how the whole absolute value thing works, especially that's going to be important when we're dealing with variables. So let's say we have the fourth root of 16x to the 5th over 81. All right, properties of roots are still going to come into play here. 16 actually happens to be a perfect fourth because 2 to the fourth power is 16, so I don't need to do anything to that. As a matter of fact, 81 also happens to be a perfect fourth because 3 to the fourth power is 81. It's the x to the fifth part that is not going to be perfect. So what we're going to do is we're going to split this up to be the fourth root of 16 times the fourth root of x to the fifth over the fourth root of 81. The fourth root of 16, fourth root of 81, we just talked about, are perfect. So that's going to be a 2 here. We'll have a 3 here. But I've still got that fourth root of x to the fifth. Well, you can split x to the fifth to be x to the fourth times x. And again, we'll continue our properties here. That'll be the fourth root of x to the fourth times the fourth root of x. And we can do the fourth root of x to the fourth, which really just simplifies to x. However, it's an even root and it's a variable. So what we really need to write that is not just of x, it's going to be the absolute value of x. So this is going to simplify to 2. The fourth root of x to the fourth is the absolute value of x. The fourth root of x in this one here doesn't simplify any further, and then still over 3. All right, and there's multiple ways. You could write that answer right there, but that is perfectly fine in its form. All right, simplifying some radicals, combining them if possible. So let's say that we have negative 8 square root of 12 plus the square root of 3. This is adding and subtracting. You have to have like terms. Basically, what you want to think of these roots as almost being like variables in the fact that they have to be identical in order for you to combine them. Well, the square root of 12 and the square root of 3 are most certainly not the same. But I can try to simplify and see what happens first. So we're going to rewrite that square root of 12 as the square root of 4 times 3 because 4 is a perfect square, which is going to simplify to negative 8. Oops, didn't mean to erase that. Negative 8 times the square root of 4 times the square root of 3 plus the square root of 3. And of course, that square root of 4 is 2. So that 2 times the negative 8 will give you negative 16 times the square root of 3 plus the square root of 3. And now what we have are like terms. I've got negative 16 square roots of 3 plus 1 square root of 3. So really what that leaves us with is negative 15 square roots of 3. Again, these 5s are killing me, man. Negative 15 square root of 3. So it's basically just like combining variables. So we can do that. We can use the idea of these roots to rationalize denominators, rationalize expressions. Let's change colors here. Let's do something different. So a very basic one is 1 divided by square root of 3. I could go into why it's necessary to do this, but we'll do that at a different time. But in order to rationalize this, what we're trying to do is we are trying to rationalize the denominator. In other words, we're trying to get rid of the root from the denominator. Well, in order to get rid of a square root, you should multiply it by the same square root. So we need to multiply that denominator by the square root of 3, but of course you can't just do that on the bottom. You have to do it on the top in order to keep the fraction consistent, which means then you get the square root of 3 over, technically that is the square root of 3 times the square root of 3, which simplifies to the square root of 3 squared, or just 3. You could also think of that as the square root of 9, which is also 3. Not quite as easy to do when it comes to cube roots and so on, but should those come up, we'll deal with it. And you know what? Let's go ahead and do one just to make sure we've got it. So let's do 5 over 4 cube root of 4. In order to rationalize that, we have to get rid of that cube root of 4. There's a couple of different methodologies here to do this. What you're trying to do is, because we're trying to get rid of a cube root, you don't just multiply it by the same cube root. That doesn't work. What you want to do is you want to create underneath of the root a perfect cube. So what you want to ask yourself is, what cube root would I have to multiply on the top and the bottom so that the cube root on the denominator becomes a perfect cube? Well, if you multiply the denominator by the cube root of 2, now multiplying those two cube roots together would give you the cube root of 8, which simplifies to a non-radical number. So we'll write this out now as 5 times the cube root of 2. I'll actually write it out in multiple steps here. And then 4. This now becomes the cube root of 8. And of course, the cube root of 8 is 2. So we get 5 cube root of 2 over 4 times 2, which is 8. All right, and the last example we'll do as far as rationalizing for now anyway, is going to be if we have something like square root of 2 over square root of 3 minus 3 square root of 2. This one actually becomes a pretty important concept. You notice you have two different square roots in the denominator, and they are being either added or subtracted, so that creates an issue. So the idea is, in order to get rid of these, what we want to do is we want to multiply by what is called the conjugate of the denominator. And a conjugate is basically the exact same two terms here, but with an opposite sign in the middle. So I'm going to multiply the numerator and the denominator by the square root of 3 plus 3 square root of 2. Square root of 3 plus 3 square root of 2. And let's see what happens in the denominator first, just so you have an idea. So if you were to FOIL these, again, we'll pretend like these things are in parentheses. Technically they are, we just don't usually write them. That first one times the first one, square root of 3 times square root of 3 is just 3. Now, if I were to multiply the outside pieces here, that's 3 times the square root of 2 times the square root of 3, which basically becomes 3 times the square root of 6. If I multiply the inside pieces, that is also a 3 times the square root of 6, but it's negative. So I have a positive 3 square root of 6 and a minus 3 square root of 6. Well, those two things subtract away. So then if I multiply the last two pieces together, I'll get a minus 9 square root of 4, which is the same thing as 2. So you can see that those two things actually work out to get rid of the radicals in the denominator. So let's go ahead and finish this one off. The numerator is going to end up being, let's see, distributing that square root of 2 to both things will be a square root of 6 plus 3 times the square root of 2 times the square root of 2 is 3 times 2, which is 6. So we get the square root of 6 plus 6, and then 3 minus 18 is negative 15 in the denominator. And that's about as simplified as that one gets. All right, so now we're going to talk about rational exponents as far as how to simplify numerically, and then we'll use some variables as well. And I apologize if you notice that I keep pausing this thing. It's because I'm actually recording this during the middle of a storm and my power keeps going out. The good thing is my laptop seems to have enough power, so I think we'll muscle through this thing. And then we'll see how, if I can upload it or not. But that's why I keep doing it. Kind of feel like that commercial, if you've ever seen that commercial with the two kids sitting at the table, and the one kid says, "Hey, the power goes out and I can still do my homework," and the little girl says, "Who are you? Like, why would you want to do that?" Well, I feel like that little boy. I'm like, "Yay, I can still do this." Anyway, all right. So what example are we on here? Let's see. We'll do example 4. which will be a couple of multiple things here. Something as easy as if I wanted to take 4 to the 3 halves power and simplify that. Remember, the idea behind that is the power is the exponent, the numerator, and the root is the denominator. So this is a 2 for a root, so it's a square root of 4 raised to the third power. But you don't have to write it in that order. You can rewrite this instead as the square root of 4 and then raise that answer to the third power. So the order that you do the exponent doesn't really matter. You can do it as the power first and then take the root, or you can do the root first and then take the power. As I've said before, I think it makes it easier to make things smaller before you make them bigger, because I can do the square root of 4 easily, which is 2, and then raise that to the third power, which is 8. Of course, we could have done it the other way around. 4 cubed is 64, and then the square root of that is also 8. Still works. But again, a lot of times when doing this, it makes it easier to do the root first. For example, if I had 25 to the 6/4 power. Now, as it stands right there, one, I don't know what the fourth root of 24 is off the top of my head, and I certainly don't want to raise 25 to the 6 without using a calculator, that's for sure. Certainly don't know that one. But you also should notice that the exponent 6/4 reduces, which you should always try to do first anyway. So we're going to rewrite that as 25 to the 3 halves power, which then, once again, I could raise 25 to the third. I happen to know what that one is, but probably not something you want to have to do in general. So what we want to do is we want to take the square root of 25 first and then cube that answer. So if you take the square root of 25, which is 5, and then cube it, you get 125. Again, probably easier than raising 25 to the third power and then trying to figure out what its square root is, because you probably wouldn't know that one too easily off the top of your head. All right, for our next example, we're going to take something that looks like this. 9x squared y to the 1/3 divided by x to the 1/3 y. We're going to raise that whole thing to the 1/2 power. So there are multiple ways you could go about doing this, and really this just becomes a feel thing, like how do I feel most comfortable doing it. Technically, you could simplify everything that's on the inside of the parentheses first, because everything in here is being multiplied or divided, so everything simplifies. Or you can go ahead and distribute that 1/2 power throughout every term. It doesn't really make any difference. Personally, I like to simplify first and then raise to exponents. So my thought is, let's go ahead and simplify what's on the inside first. So I've got an x squared divided by an x to the 1/3. So if you remember properties of exponents, it says that you basically take the exponent, since you're dividing the bases, and subtract the exponents. The 9 isn't going to do anything. There's no constant, so it stays where it is. Then the x is going to be x squared over x to the 1/3, which is going to be a 2 minus 1/3. 2 minus a third is actually going to be 5/3. So that'll become x to the 5/3 power. And then the y to the 1/3 divided by y, which is y to the first. So 1/3 minus 1 is going to be negative 2/3. And all of that still has to get raised to the 1/2 power. So now what we do is we distribute the 1/2 power to be the power of everything on the inside. Again, this works because everything is multiplied or divided. There are no additions and subtractions. If there are, you cannot distribute the power. So technically, this will be 9 to the 1/2. When you distribute a power to a power, you multiply the powers together. So 5/3 times 1/2 will be 5/6. And then negative 2/3 times 1/2 will be negative 2/6, which reduces to negative 1/3. And the only other thing we want to do, because we are simplifying, is we don't want negative exponents. And because we have a y to the negative 1/3, that drops the y part down to the denominator, which we currently don't have, but we will create. And 9 to the 1/2 is the square root of 9, which is the same thing as 3. So we get 3 x to the 5/6 divided by y to the 1/3. And that is that in its simplest form. All right, last example for this extremely long section. What we're going to do is we are going to factor this expression. All right. And you might look at that and think, how in the heck am I going to factor that thing? So there are multiple things that you can do. So if you think about an expression, something very simple like, let's just say we've got 2x to the third plus 4x squared, and you want to factor that, you would look to see with your coefficients, is there anything in common? Obviously, I have a 2 in common that I can factor out. With the exponents, do I have anything in common? Yes, I have an x squared in common, which I can factor out, which would leave you with an x and then plus 2. So that would be how you would factor it with whole number exponents. With this, it's the same principle. The main difference is what you have to figure out is when I factored the variable, the biggest exponent of factors that I could pull out was an x squared, because you can't pull out more than x squared from that 4 term. That's the biggest thing you could factor out of there. What you're doing is you're looking for basically what would be that smallest exponent of the x's. That's the most that you can pull out. It's going to be exactly the same idea in this. When we factor this, we're looking for the smallest exponent of the x's. In this case, 1/3 is the smallest exponent. Technically, there's more I can factor out as well, because I also have a 2 and I have a 4 in the exponent here, which I can actually factor a 2 out of that. So let's go ahead and do that. If I factor the 2 out, that's your constant, I'm going to factor out an x to the 1/3. All right, let's see what that leaves us with. So if I factor the 2 out of the 4/3, basically you're dividing it out of the 4/3. So 2 times 2/3 would give me that 4/3. So that's what that gives you there. I factored the x to the 1/3 out, so it's gone from that term. I still have a 2x plus 1 left over there. Okay, I factored the 2 out of that second term. And now when you factor the x to the 1/3 out of the x to the 4/3, remember the idea behind factoring is you're dividing, you're undoing a distributive property. So you would want to think of this as being x to the 4/3 divided by x to the 1/3. And once again, when you divide those common bases, you subtract the exponents. So 4/3 minus 1/3 is 3/3, or just 1. So I am left with x right there. So then I can simplify a little bit. That'll be 2x to the 1/3. I can distribute that 2/3 through there, and we're going to get 4x over 3, or let's write it as 4/3 x, plus 2/3 plus x, and then I can combine the two x's on the inside. So we're going to get 2x to the 1/3 power. The 4/3 x plus another x in terms of thirds will give you 7/3 x plus 2/3. And I guess technically now I can go ahead and factor out another 1/3, I guess. So let's do that. That would give me a 2/3 on the outside, x to the 1/3, and then 7x plus 2 on the inside. And I think that's probably the most simplified form of that. There is going to be pretty much an entire worksheet that will be posted that is practice for this type of stuff, factoring these things using common factors to simplify. Again, a very long video. I apologize, but that does finish up our section for 1.3.